A clock's hands slow down. They slow until they stop. They freeze forever at the edge of a supermassive black hole. Inside these things, these cosmic monsters, our most basic idea of order just dissolves. It turns into pure chaos, so time becomes meaningless. That's the mystery. You start with Einstein's insights. You go to the latest simulations. You see the universe's strangest behavior. What would you actually experience? Time distorts. It distorts beyond all recognition. Reality itself breaks down. The rules of cause and effect, they vanish. You're journeying into an abyss. Physics as we know it ends there. And what does that mean? If time can just stop, what does that mean for our own reality? We've always experienced time as something that just moves forward, unstoppable. The Greeks imagined Kronos, this titan who ate his own children, that idea of time consuming everything, always advancing. And that's how it feels, a one-way street, sunrise to sunset, the clock ticking. But physics shows us something much weirder. Time isn't some universal river, the same speed for everyone. It's actually a dimension woven together with space into one fabric spacetime. In everyday life, you don't see that weaving. Time feels absolute, like Newton thought, just a steady background. But Einstein showed that background is flexible. It can stretch, it can compress. His relativity told us time is relative. How fast it passes depends on your speed and how close you are to gravity. A clock on a fast spaceship ticks slower than one on Earth. A clock near a massive planet ticks slower than one farther out. And that's not some error, that's how reality actually works. We use this fact every day. GPS satellites orbit high up where gravity is a little weaker. Their clocks run faster, just a tiny bit, compared to clocks on the ground. If engineers didn't correct for that time dilation, your navigation would be off by kilometers in minutes. So what is time then? Carlo Rovelli has this provocative idea: time is ignorance. It's the measure of what we don't know about the microscopic state of things. We sense an arrow of time because of entropy, the universe's drift toward disorder. We remember the past, not the future, because the past had lower entropy. But in the basic equations of physics, time often has no preferred direction. That's the delicate framework we live inside, a mix of measurable intervals and deep mystery. We think we understand its rules, that consistent tick, but that understanding is local, a kind of calm inside a much wilder cosmos. And it's that very framework, that illusion of steady flow, that a supermassive black hole doesn't just bend, it shatters it completely. That idea of a single, steady clock for everyone, that ended with one man's happiest thought. Albert Einstein, working at the patent office, he pictured someone falling, maybe off a roof, and in that fall they'd feel weightless. For them, gravity would just disappear. That equivalence between acceleration and gravity became the foundation, the cornerstone of his general relativity. It rewrote everything. Gravity wasn't some force acting at a distance. It was geometry, the geometry of the universe itself. Think of a trampoline, fabric stretched tight. Put a heavy bowling ball in the middle, the fabric warps. It curves, now roll a marble near the edge. It spirals in, not from some invisible pull. It's just following the path, the curve made by the bowling ball. That trampoline fabric is spacetime, a single thing. It fuses the three dimensions of space with the dimension of time. Mass and energy, like that ball, tell spacetime how to curve. And that curvature tells everything else how to move. That's the marriage, space and time. They're not just a stage where things happen, they are the stage. And the stage can bend, it can stretch, it can ripple. That geometric view has a consequence for time. If spacetime is curved by mass, then time has to run at different rates. In different places, that's gravitational time dilation. Clocks tick slower where gravity is stronger. We've measured this, the Pound-Ribka experiment, in the late 50s. It measured a tiny shift in light frequency, just from climbing 22 meters against Earth's gravity. Today, the atomic clocks on GPS satellites have to be corrected for it. Or your map would be wrong in minutes. An astronaut on the space station, where Earth's grip is weaker, ages a tiny fraction of a second slower than we do. It's not a quirk, it's the literal reality, time as part of a flexible fabric. Einstein wrote about this strangeness in a letter. He said the distinction between past, present, and future is only a stubbornly persistent illusion. In relativity, your whole life, from birth to now, can be described as a world line, a single, unchanging path woven into spacetime. The math for this curvature is the metric tensor. A complex set of numbers, it defines the distance between every point in that four-dimensional continuum. That geometry dictates everything, the orbit of planets, the bending of starlight. So if gravity is geometry and that geometry dictates the flow of time, then what happens when the curvature becomes infinite? Not just steep, infinite, that's the key, the essential key that unlocks the black hole's door. If time is part of a fabric that can be warped, what does it mean when that fabric is stretched to its absolute limit? Can the thread of time itself be torn? That infinite curvature, that's the mark of a monster. And there's one sleeping right at the center of our own galaxy, the Milky Way. Sagittarius A star. For a long time, it was just this strange, powerful radio signal, a mystery at the galactic core. Then, in 2002, Andrea Ghez and her team tracked stars orbiting an invisible point. They were moving at over 5,000 kilometers a second, and their paths proved it. There was an object there, 4 million times the mass of our Sun, squeezed into a space smaller than our solar system. Only one thing fit, a supermassive black hole. Ghez called it an inescapable grip on spacetime. A grip so deep it doesn't just capture stars, it shapes the entire galaxy's structure. But not all black holes are like that. The ones we usually talk about are stellar mass black holes. They come from a massive star collapsing at the end of its life. Maybe 10, 20, 50 times the Sun's mass. They're powerful, but they're local. A supermassive black hole is a different kind of beast. Millions, even billions of solar masses. How does something that big even form? The main theories go back to the early universe. In that first darkness, huge clouds of primordial gas might have collapsed straight into these giants, never becoming stars at all. Or maybe they started as smaller seeds and grew over billions of years, feeding on gas and dust, merging with others when galaxies collided. They aren't just living in galaxies. They're probably why galaxies have the stable, spiral shapes we see. They're the anchors, the gravitational hearts everything else swirls around. That immense size changes what falling into one would be like. With a stellar black hole, the tidal forces are brutal. The difference in gravity between your head and your feet, it's ferocious. You'd be stretched into a long strand long before you reach the event horizon. That's the spaghettification you hear about, but with a supermassive black hole, the event horizon is so vast, the curvature is gentler. In theory, you could cross that point of no return without being torn apart immediately. The monstrous gravity is still there, of course, but it would feel like a smooth, unstoppable pull. The real violence happens deeper in. Our first real look at that shadowy realm came in 2019. The Event Horizon Telescope, a planet-sized network of radio dishes, released an image of the supermassive black hole in galaxy M87. It showed a dark central shadow, a silhouette against a ring of swirling, superheated gas. That shadow isn't the black hole itself. It's the event horizon's gravitational influence, warping light so severely it creates a perfect circle of darkness. A photograph of spacetime being consumed. Looking at that image, you're seeing the edge where all known physics breaks down. What happens inside that shadow? What does time become when it's not just bent but swallowed by that kind of darkness? To answer that, you'd have to cross the line. That dark circle is the precipice. The edge of a cosmic waterfall. Spacetime flows inward, and at this boundary, the current becomes irresistible. That's the event horizon. It's not a solid surface. It's a mathematical line in the geometry of the universe, defined by one fact. At this exact distance from the black hole's center, the escape velocity, the speed you'd need to break free, equals the speed of light. And since nothing can go faster than light, nothing comes back out. Not a particle, not a rocket, not a single photon. It's the ultimate one-way street. Stephen Hawking described this boundary with a twist. He said the event horizon is where time and space swap roles. Outside, you can move forward or backward in space, but you're always forced forward in time. That's the rule. Cross that line, and the rule inverts. Inside, your movement through space becomes a one-way trip inevitably toward the center, the singularity. But your movement through time, that might become a direction you can choose. The coordinates switch. Time becomes like a space you can navigate. Space becomes like a time you're compelled through. It's the first sign the universe's rulebook is being rewritten. From our perspective, watching from a safe distance, something else happens. As an object approaches the event horizon, its light is stretched by the immense gravity. That's gravitational redshift. The light reddens, then dims. Signals from an astronaut sending back a steady pulse would slow down. The time between pulses would grow longer. The last pulse, emitted right at the horizon, would be redshifted to infinity. Its wavelength stretched so far it carries zero energy. To us, the astronaut would appear to freeze, fading to a dim, red ghost forever stuck at the edge. Their clock from our view would stop. That creates a puzzle. If, from the outside, nothing ever seems to cross the horizon, does anything ever truly fall in? This question is at the heart of the information paradox. Quantum mechanics says information about what falls in cannot be destroyed. But general relativity, with its smooth event horizon, suggests it is. For decades, physicists argued over which law breaks. One proposed solution was the firewall hypothesis, the idea that the event horizon might not be smooth, empty space, but a searing wall of high-energy particles. It would incinerate anything trying to cross, a sign of the deep conflict between our two great theories of reality. The size of this point of no return is the Schwarzschild radius. A simple calculation depending only on the black hole's mass. For an object as massive as our Sun, that radius is only about 3 kilometers. For the supermassive heart of our galaxy, it's over 12 million kilometers across, a sphere larger than the orbit of Mercury. You could theoretically cross that vast boundary without being torn apart. But once you do, the swap is complete. You enter a realm where the forward march of time, as you've always known it, ceases to be your master. And that raises a question. If time stops at the horizon from the outside, but you, from the inside, continue to fall, what does your own clock actually show? Your clock keeps ticking. You cross the line. There's no bump, no flash. For a supermassive black hole, the event horizon is just calm. You go from one state to another. Like a boat going over the edge of a huge, dark waterfall, your instruments read normal, your own heartbeat is steady. That clock, the indestructible myth, just keeps its rhythm. From where you are, time feels normal, but if you look back at the universe you came from, the view from inside is what changes everything. The light from the outside cosmos falling in with you gets compressed. It blue shifts. It packs eons of energy into instants. The stars and galaxies don't just move away. They accelerate. Their light, carrying the story of everything that will ever happen out there, rushes toward you. You'd see the future history of the whole external universe play out in one blinding flash. Millions, billions of years, star formation, galaxy collisions, The slow fading of all suns compressed into a final burst before that light is also swallowed by the darkness ahead. Out there, time is a frenzied, rushing river. In here, for you, it's a steady stream, but that stream only goes one way. This is where Brian Greene's statement becomes real. Inside a black hole, the future isn't a possibility. It's a location, the singularity. Think of it like this. In normal life, you have a future light cone. All the points in spacetime you could possibly reach. It fans out ahead of you, full of potential paths. The moment you cross the event horizon, that cone tips. It tips completely inward. All those possible futures, every path your life could take, now converge on a single point in space ahead of you. The causal structure of reality gets rewritten. You're not navigating time anymore. You're falling through space toward a moment that is, for you, an inevitable destination. The idea of now as something shared with the rest of the universe, it shatters. Your now and the outside universes now are disconnected, separated by an unbridgeable gulf of curved geometry. So you fall. The pull is smooth, but it's absolute. The question then becomes not about physics, but about perception. Would this feel like a trap, the ultimate cage where every atom of you is on a rail to destruction? Or could there be a strange liberation in it? All choices, all uncertainties about what comes next are erased. The anxiety of possibility is gone, replaced by a terrible, singular certainty. You're riding the fabric of spacetime as it cascades toward its own breakdown. You're experiencing time not as a flow, but as a slope, a geometric incline so steep it becomes a vertical drop. And at the bottom of that drop is the greatest mystery in all of physics, the place where the waterfall of time hits the rocks, the singularity. The math of the fall is in the geometry. Einstein's equations say a clock's ticking is set by the gravitational potential where it sits. A deeper potential well means slower time. The formula from general relativity is simple. The time dilation factor depends on 1 minus 2 times the gravitational constant times the mass, divided by the speed of light squared times the distance. As that distance gets smaller, heading toward the event horizon, that term in the equation gets closer to zero. And when you divide by something approaching zero, the result goes to infinity. That's the extreme of gravitational time dilation. For someone watching from far away, a clock falling toward a black hole, each tick takes longer to arrive. The signals stretch, the clock seems to slow, and right at the event horizon, the time between ticks, seen from outside, becomes infinite. 1 second for the person falling could be an entire age of the universe for those watching safely. Simulations show this. They show a probe's last signal, maybe a heartbeat of data, redshifted into oblivion. Its frequency drops to nothing over what for us would be eons. The outside universe sees the fall as a freeze frame, a moment preserved forever. To see this, you look at the Schwarzschild metric. That's the math for spacetime around a non-rotating black hole. In it, there's a term that controls the flow of time. That term goes to zero exactly at the event horizon. What that means is the link is broken. The link between coordinate time, time for a distant universe, and proper time, time for the traveler. The traveler's proper time keeps a finite rhythm all the way to the singularity. But to translate that rhythm into the coordinate time of the outside world, you have to divide by zero at the horizon. It's a mathematical asymptote, a point where our description of reality hits a wall. This isn't just theory. We see milder versions every day. The precise clocks on pulsars spinning neutron stars. Their rhythms are minutely changed by their own intense gravity. We have to account for that dilation to use them as cosmic lighthouses. The effect is real. A black hole just takes it to its logical conclusion, and it's terrifying. Think of the classic twin paradox, but with a black hole. One twin stays in a safe orbit, watching from a distance. The other twin descends toward the event horizon. From the orbiting twin's view, the descending twin slows, fades, never quite crosses the line. Their timelines once shared are split now, irrevocably. The falling twin's personal journey continues, but from the outside universe's frame, that journey's conclusion is pushed infinitely far into the future. They can never meet again to compare clocks. Their shared now is lost. That forces a question, almost a philosophical one. If, from the perspective of the entire external cosmos, time effectively stops for anything at the event horizon, does the interior of the black hole exist at all in our universe's timeline? Or is it a separate reality, a bubble of spacetime pinched off from our own causal flow? This infinite dilation isn't just a curiosity. It's the first fundamental crack in the foundation of time as a universal experience. It shows time as a local phenomenon, dependent entirely on where you are and how you're moving. And if time can be stretched to infinity, then maybe it can be twisted into something else entirely. That mathematical asymptote is a signpost. It tells us the map we're using is wrong. Schwarzschild coordinates, they break at the horizon. They're like a flat map of the Earth that distorts the poles into lines. Useful far away, but they fail at the boundary. To understand what happens inside, you need a new map, one that doesn't tear. The Kruskal-Szekeres coordinates are that map. They're the mathematical equivalent of a globe for a black hole. They cover the entire geometry smoothly from the faraway universe across the event horizon, all the way down to the singularity. And what they show is the core strangeness. Inside the event horizon, the roles of space and time swap. Think of it like this. Out here, you are always moving forward in time. You can't help it. You can stand still in space, but you are swept from one second to the next. That's the nature of time for us. A one-way flow, now, cross the event horizon. The Kruskal map shows that inside, the radial direction, the line pointing straight toward the black hole's center, becomes timelike. That means moving toward the center is as unavoidable as moving from Monday to Tuesday is for you right now. And what was the time coordinate outside becomes space-like inside. You can move through it like you move left or right. This is the space-time role reversal. As physicist Leonard Susskind put it, inside, space falls like time flows. Your future is no longer a spread of possibilities. It is a specific location. The singularity, it's not a place you can avoid like a wall. It is a moment in time that will happen to you. Imagine being on a conveyor belt in a vast, dark factory. The belt only moves in one direction. You can walk forward or backward on the belt. You can run sideways along its edges, but the belt itself is carrying you inexorably toward a giant press at the end. Your personal effort is meaningless against that transport. That's what falling is like inside a black hole. You are on the conveyor belt of spacetime itself, and it is flowing inward at the speed of light. You cannot stop, you cannot even hover. The concept of a stationary orbit, like a satellite around Earth, ceases to exist. Every possible path leads to the same destination. This is seen in the light cone structure. Outside, your future light cone points broadly outward into the universe. The moment you cross the horizon, that entire cone tips. It tips until it points exclusively toward the singularity. Every photon you emit, every signal you could send, goes inward. There is no out anymore. All futures converge, so if space acts like time, can you ever stop falling? The answer is no. It's a no written into the fabric of reality itself. Trying to stop your fall toward the singularity would be like trying to stop Monday from turning into Tuesday. You are not fighting against a force, you are fighting against the structure of causality. You are embedded in a geometry where toward the center is the only definition of future. This role reversal dismantles our intuitive separation of space and time. They merge into a single, fatal trajectory, and at the end of that trajectory, where the conveyor belt drops into the abyss, lies the singularity. A point where our understanding doesn't just bend, it vaporizes. The conveyor belt of spacetime just drops into the abyss, and at the end our equations scream. They give us infinities, density goes infinite, curvature goes infinite, temperature infinite. It's like asking a calculator to divide by 0, it just flashes error. That's the singularity. The Penrose and Hawking theorems proved it's inevitable. Under that pull, under gravity inside a black hole, all matter has to collapse. Collapse to a point of 0 volume. There's no physical force we know that can stop it. The singularity isn't just a place of extreme conditions, it's a boundary. The boundary where the ideas of where and when, they lose all meaning. Hawking said it starkly. He said the singularity is where time itself begins and ends. Think about that. Your whole journey inward, time was still a dimension you moved through. Even warped at the singularity, that dimension stops. There's no before it. No after it, not in any conventional sense. It's the edge of the spacetime map, like the old maps that said here be dragons. Our physics map just ends. The coordinates we use to navigate reality, they dissolve. That's why general relativity fails. Its beautiful equations, they describe the curvature of spacetime perfectly everywhere else. But they break down when the curvature becomes infinite. The theory predicts its own limits. It tells us we need a new physics, a theory of quantum gravity. To describe what happens at that scale, we have to separate two ideas here. A coordinate singularity is like the North Pole on a map. All lines of longitude meet there. It seems strange, but it's just an artifact of our grid. The true curvature singularity at the black hole's heart is different. The curvature itself becomes infinite. A real physical blow-up in the fabric of reality. What's it like to approach that boundary? Some models, like the Becquerel conjecture, suggest chaos. That's Belinsky, Kolotnikov, and Lifshitz. They propose that as you near the singularity, the geometry of space starts to oscillate wildly, chaotically in different directions. It would be less like falling toward a point, more like being tumbled in a cosmic dryer, space stretching and compressing in violent, unpredictable ways. That's the ultimate breakdown of order, so we're left with a question. Almost a philosophical one. If time has no meaning at the singularity, do before and after have any hold there? Is it a moment of destruction, or is it a transformation so complete that our language for events just doesn't apply? This is the destination where all paths converge, and all meaning as we understand it is lost. But what if loss isn't the end of the story? What if this apparent end is actually a door? That final breakdown of order leads to something even stranger, the loss of causality, the idea that effect can come before cause. You can picture a domino chain, but the pieces fall in any order. The 10th domino could knock over the first. The effect creates its own cause. It's a closed loop. Inside the black hole, this isn't fiction. It's a mathematical possibility. It's embedded in the warped geometry. If an event can happen before the thing that caused it, then what does reality even mean? This violation comes from those tilted light cones. As you fall deeper, the tilt becomes so severe. The paths of possible influence, the world lines, can theoretically bend back on themselves. They can form a loop, a closed time-like curve. It's a theoretical path through spacetime that returns to its own starting point. In space and in time, you could, in principle, travel along it and meet your younger self. The physicist Igor Novikov studied these paradoxes. He proposed a way to avoid the worst logical knots, a self-consistency principle. The universe might enforce it. Any action taken on a closed time-like curve would have to be consistent. You couldn't change the past to create a contradiction. You were always part of the event. If you go back to prevent an accident, your attempt to prevent it might be the very thing that causes it. The timeline is fixed. These curves aren't just speculation. They appear in solutions to Einstein's equations for rotating black holes described by the Kerr metric. The intense spin twists spacetime into a complex vortex. These closed loops can, in theory, form inside a region, the inner horizon or Cauchy horizon, but this region is unstable, notoriously unstable. The slightest perturbation, a single particle of dust falling in, could trigger a runaway feedback of energy. A phenomenon called mass inflation that might destroy the structure or shield it from entry. It's a mathematical frontier that may not be physically reachable. The conflict here is profound. Quantum mechanics, the rules of the very small, is built on unitary evolution. Information is preserved. Processes are predictable in a forward-moving sequence. Closed time-like curves shatter that sequence. They create paradoxes that break quantum rules. The classic example is a message sent to your own past. You receive a note with schematics for a time machine. You use those schematics to build the machine. You go back in time and give the note to your younger self. Where did the information in the note come from? It was never created. It just exists in a loop with no origin. This isn't just a puzzle about notes. It's a puzzle about existence itself. To prevent this, Stephen Hawking proposed the chronology protection conjecture, the idea that the laws of physics conspire to make time travel to the past impossible. On a macroscopic scale, quantum effects like virtual particles flooding the region might create an impenetrable barrier, an infinite energy barrier. A kind of quantum firewall for time that destroys any closed time-like curve before it can be used. The universe, in this view, has a built-in defense mechanism against paradox. So we're left with a question. If causality fails, can any event truly be said to have a definite time? Our entire experience of reality is built on a sequence. This happened, then that happened because of this. That sequence gives time its narrative meaning. It's the thread that turns a series of moments into a story. Inside a black hole, that thread is cut. The story unravels. Events float in a sea of potential, unmoored from before and after. This is the ultimate erosion of meaning. Not just the stopping of a clock, but the dissolution of the logical framework. The framework that makes a clock's reading signify anything at all. The logic of sequence just dissolves. And you're left with this question about what an event even is. That brings in a fifth principle, maybe the most disorienting one. Time inside a black hole depends on who's looking. Think about two people watching a sprint from different angles along the finish line. One sees a photo finish, too close to call. The other, from a side view, sees a clear winner by a full stride. They disagree on what happened when. That disagreement, that relativity of simultaneity from Einstein's special relativity, gets amplified to an extreme by the gravity of a black hole. There is no single, universal now inside that darkness. The passage of time, the ordering of events, gets locked to your personal perspective, your state of motion. Your location. Einstein wrote that the time of an event is not absolute. It depends entirely on the reference frame. To navigate this, physicists use different coordinate systems. Like different languages for the same landscape, Eddington-Finkelstein coordinates are one such language. They let us chart the journey smoothly from the outside in. And what they show is striking. An observer falling through the event horizon and a distant observer watching from safety will assign completely different times to the very same event. For the distant watcher, your crossing of the horizon is an event forever in their future. It never quite happens in their now, but for you, the traveler, it's a moment you pass through at a specific, finite time on your watch. Both perspectives are correct within their own reference frame. There's no referee to say which clock shows the true time. This touches the idea of hypersurfaces of constant time. In our normal world, we can imagine a three-dimensional slice of the universe, a snapshot of now that everyone could, in principle, agree on. Inside a black hole, that concept breaks down. You can't draw a single slice that represents now for both the inside and the outside. Their nows are fundamentally disconnected. This supports the block universe interpretation. where all of spacetime past, present, and future exists as a single, four-dimensional block. Your journey is a fixed world line within it. From a God's eye view outside the block, your entire life, from birth to the singularity, is just a thread. But from within, you experience that thread moment by moment. The black hole violently separates which moments you experience from which moments anyone else can ever witness. Take two perfectly synchronized atomic clocks, place one in a laboratory orbiting far from the black hole, send the other plunging inward. The moment the falling clock crosses the event horizon, their synchronization isn't just broken, it's rendered meaningless. The laboratory clock will never receive a signal from the moment of crossing. For the lab, the falling clock's time effectively stops at the horizon. For the falling clock, its own time continues ticking down toward the singularity. They are no longer describing the same flow. They're telling time in two different, incompatible realities. Near the singularity, this subjectivity reaches a kind of quantum fever pitch. The wild oscillations of the Becquerel chaos would make the very concept of a clock ambiguous. A clock measures intervals of time, but if spacetime itself is churning unpredictably, what stable rhythm is left to measure? The tick of a clock depends on a regular, repeating process. In that final maelstrom, regularity itself may vanish, so you have to ask, if time is so utterly dependent on who is measuring it and where they are, can we say it exists as an independent thing at all? Or is it, at its most fundamental level, a relationship, a story we tell about change and connection? Inside a black hole, that relationship is severed. Time becomes not a shared river, but a personal, isolated stream. A stream that flows only for you until even that private current is lost. That personal stream of time it dissolves into quantum foam, the smooth fabric of spacetime, the tapestry from Einstein's equations it can't hold. Not at the smallest scales. There, it becomes a frothing sea. A probabilistic sea of fluctuations. That's the conundrum. General relativity says time ends at the singularity. It's a final period. But quantum mechanics, our other pillar, insists on a different rule. Unitary evolution. Information about what falls in can never be truly lost. It's preserved, scrambled maybe, but never erased. So you have two foundational theories. They give us two contradictory endings to the same story. To find the truth, you need a theory that unites them, a theory of quantum gravity, and in those tentative theories something happens. Time might not end, it might be reborn. Theorist Lee Smolin proposed a radical idea. Time may not be fundamental, it could be emergent, like temperature emerges from the motion of countless molecules. The smooth flow of time might emerge from more fundamental, timeless processes. Imagine a crowd in a plaza, each person moving randomly. From a distance, you see a smooth, flowing current. That current is time emerging from the chaos beneath. That shifts the entire question. We're not looking for how time stops, we're looking for how it arises. Several paths lead into this. String theory offers the Fuzzball conjecture. It proposes that what we call a black hole's interior, it isn't empty space leading to a point. Instead, the entire region is filled with a gigantic, tangled ball of strings. The fundamental threads of reality, a quantum fuzzball. There is no sharp singularity. No point of infinite density. The information about what fell in is smeared throughout this complex quantum state. In this view, an astronaut crossing the horizon wouldn't encounter empty space. They'd merge with this quantum tapestry, their own information becoming part of the fuzz. Time, as a classical concept, might break down, but the quantum evolution continues. Another path comes from loop quantum gravity. This approach suggests spacetime itself is woven from tiny, discrete loops, a fabric with a finite weave. In this picture, the immense density of a singularity can't be infinite, because you can't pack energy into a volume smaller than the smallest quantum of space. Instead of a collapse to nothing, the equations point to a bounce, a super-dense region would rebound, perhaps giving birth to a new region of spacetime. In loop quantum cosmology, our own universe might have begun from such a bounce. Inside a black hole, this could mean the singularity is a bridge, a gateway to somewhere or someone else. The conveyor belt of spacetime doesn't end in a shredder. It might curve into a new tunnel. Connecting these ideas is the holographic principle. It's one of the most profound insights. It suggests all the information describing the three-dimensional interior of a black hole is perfectly encoded on its two-dimensional event horizon. Like a complex three-dimensional image stored on a flat, two-dimensional film, the interior, with all its apparent chaos, is a projection, a shadow cast by quantum data on the surface. If this is true, then the passage of time inside might also be a kind of projected story, an emergent narrative from timeless data on the boundary. This brings us to a deep equation. The Wheeler-DeWitt equation. It attempts to describe the universe in quantum gravitational terms, and it has a startling feature. The time variable drops out completely. The equation describes a static, timeless quantum state of the entire cosmos. Within this framework, our experience of time flowing could be an illusion. A compelling, persistent illusion, generated by how we, as complex systems within the universe, interact with this frozen quantum whole. Think of it like a single, unmoving frame of a movie. We are the light passing through it, experiencing one scene after another, creating the story of sequence from a static picture. So what happens inside the black hole in this quantum view? The geometries themselves could exist in superposition, multiple possible configurations all at once. The smooth, classical path of falling would give way to a quantum haze of possibilities. The astronaut wouldn't follow a single line. They'd branch into a cloud of potential histories. It's like ice melting into water. The solid, predictable structure of classical spacetime, with its definite past and future, melts into a fluid quantum state, where all directions are possible. From that fluid, a new kind of order, a new kind of time might recondense. Could time be an illusion that reforms inside the black hole? The frontier of quantum gravity suggests it might, meaning the causal sequence that makes our reality comprehensible might not be destroyed in the chaos. It could be transformed, recycled. The quantum foam from which our smooth time emerged might, in that ultimate pressure cooker, give birth to something new. A different kind of rhythm, a different kind of story. This isn't a return to normalcy, it's a metamorphosis, and if time can be reborn from its own ashes, what does that say about the nature of reality itself? That quantum fluid, it points to something deeper, a kind of hidden code, and that code rewrites what we think is real. Back in the 90s, physicists Gerard T. Hooft and Leonard Susskind proposed something. It was almost unbelievable. They were inspired by black hole thermodynamics. They suggested the holographic principle. It says all the information inside a volume of space, every particle, every force, the whole three-dimensional scene, can be fully described by information stored on its two-dimensional boundary. For a black hole, that boundary is the event horizon. It's like the three-dimensional world you experience is a projection, a hologram, like a 3D movie that's actually encoded on a flat 2D screen. Susskind said it well. He said the 3D world is an image of data stored on a distant 2D surface. This isn't just a metaphor, it has a precise mathematical form. The anti-de Sitter/conformal field theory correspondence, add S/CFT, it comes from string theory. It says a universe with gravity in a certain higher dimensional space is completely equivalent to a quantum field theory without gravity living on its lower dimensional boundary. Think of it this way. A complex, swirling black hole in a five-dimensional space could be perfectly described by a hot, chaotic quantum system living on a four-dimensional surface that surrounds it. There's no gravity in that surface description, no curved spacetime, just quantum particles interacting, yet it encodes everything happening inside the gravity-filled bulk. Including the flow of time, this gives us insights about the black hole's interior. The information that makes up an astronaut falling in isn't lost inside. It's scrambled and stored on the horizon's surface. The entanglement entropy of the horizon, a measure of its quantum connections, is directly proportional to its area. Not its volume. That was Stephen Hawking's great clue. The entropy, the information content, scales with the surface area. That's the first hint the true degrees of freedom live on the surface. Then there's the ER equals EPR conjecture, proposed by Juan Maldacena and Susskind. It suggests quantum entanglement, that spooky connection between particles, might be physically connected by microscopic wormholes. Einstein-Rosen bridges, so two entangled particles, no matter how far apart in our 3D view, could be linked by a shortcut through a higher dimensional space. Inside a black hole, this implies the fabric of spacetime itself might be woven from a vast network of quantum entanglements. The smooth geometry of the fall is an emergent picture from countless tiny quantum threads. So what does this mean for time? If the interior is a holographic projection, then the passage of time inside the black hole is also a projection. It's not a fundamental flow. It's an emergent story generated by the evolution of quantum data on the horizon's surface. Imagine a giant pixelated screen. Each pixel is a quantum bit of information. The screen flickers and changes in a complex, chaotic dance. From that two-dimensional dance, our three-dimensional brains, or our theories, construct the illusion of a continuous, flowing time inside the volume. The ticking of a clock, the feeling of falling, the approach to the singularity, all of it could be a narrative generated by timeless data being processed on the boundary. This forces a radical shift. We've asked where time goes when it becomes meaningless. The holographic answer is it never existed there in the fundamental sense to begin with. Its reality, its meaning, resides on the surface, in the quantum correlations and computations happening on the event horizon. The interior's time is a derived quality. An echo. If this is true, then the terrifying singularity might not be a place of infinite destruction, but a region where the holographic projection breaks down. Where the pixels of the screen can no longer sustain the coherent image of a spacetime continuum. So we're left with a question. If time is a hologram, is its relentless forward march, its sense of causality and narrative, just a collective illusion? A story we tell because we are embedded within the projection. The holographic principle doesn't make time less real to our experience, but it suggests its ultimate source is somewhere else entirely. Not in the depth of a cosmic pit, but on its shimmering, information-dense surface. A surface where every bit is a letter in the code of reality. And if time's reality is on the boundary, what other fundamental aspects of our universe might also be waiting there, encoded in a simpler, stranger language? That holographic surface shimmering with information, it's not just a screen, it's a ledger, a cosmic ledger for disorder, and disorder is what drives time's arrow. You take a steaming cup of coffee, you leave it on the counter, it cools, the heat dissipates into the room, that increases the overall disorder of the universe, the entropy. And that process is irreversible. You never see the heat flow back from the room into the cup, reheating it. That relentless increase in entropy, that's what gives time its direction. For a long time, physicists thought this didn't apply to black holes. How could a region of pure gravity have disorder? Then, in the early 70s, a graduate student named Jacob Bekenstein made a proposal. He said if the second law of thermodynamics is universal, if total entropy never decreases, then black holes must have entropy themselves, and not just a little. He said their entropy should be proportional to the area of their event horizon. It was a radical idea. Stephen Hawking dismissed it at first, because if a black hole has entropy, it must have a temperature. And anything with a temperature must radiate, but black holes by definition don't radiate, they're black. Hawking set out to prove Bekenstein wrong. But his calculations led him somewhere else. He found that when you apply quantum mechanics to the curved spacetime at the event horizon, something happens. The intense gravity can create pairs of virtual particles, one with positive energy, one with negative. Normally, they annihilate instantly, but at the horizon, one can fall in while the other escapes. The one that falls in has negative energy, so it reduces the black hole's mass. The one that escapes carries positive energy away. To a distant observer, this looks like a faint thermal glow coming from the black hole. Hawking radiation. Hawking said, black holes ain't so black, they have a temperature, and they slowly evaporate. Over timescales far longer than the universe for a stellar one, but they evaporate. That cemented Bekenstein's insight. The entropy of a black hole is precisely 1/4 of its horizon area in Planck units, a number so vast it makes the black hole the ultimate repository of disorder. So there's this link now. Time's arrow, driven by increasing entropy, is tied to the geometry of spacetime. When matter falls in, the entropy of that matter seems to vanish. But the black hole's horizon area increases. Its own entropy rises to compensate. The total entropy of the universe still goes up. Time's arrow marches forward. But Hawking's discovery created a paradox. The radiation he predicted is purely thermal. It carries no information about what fell in. It's like the featureless heat from a stove coil. If a black hole evaporates completely, leaving only this random radiation, what happens to all the information, the star, the planets, and astronaut? It would be lost. That violates a core tenet of quantum mechanics unitarity. Information must be preserved. It can be scrambled but never erased. That's the black hole information paradox. It pits general relativity against quantum mechanics. To visualize it, think of a log burning. The log has a specific structure, the grain, the knots. As it burns, it turns into ash, smoke, and heat. The ash seems random, but in principle, if you could collect every particle of ash and smoke and trace every photon of heat, you could reconstruct the log. The information is preserved, just transformed. Hawking initially argued that for a black hole, the radiation is the ash, but the log's blueprint is gone forever. Recent work using tools like the Holographic Principle suggests he may have been wrong. The Page curve, developed by physicist Don Page, describes how the entropy of the radiation should behave if information is eventually returned. It should rise at first as the black hole radiates, then peak, and finally decrease as the radiation begins to reveal the encoded information of the interior. Cutting-edge calculations in quantum gravity now show this curve can emerge. The information seems to be scrambled onto the horizon and slowly leaked back out in the radiation. So what does that mean for time inside the void? If a black hole evaporates, does time's arrow inside it reverse? Not exactly. Thermodynamics ties time's meaning to the flow and preservation of information. Even in the deepest darkness, that flow appears to continue. The chaotic interior, the quantum fuzzball, the holographic surface, they're all part of a vast computational process that never loses a single bit. Time's arrow may bend, it may warp, it may seem to dissolve into quantum foam, but the ledger of the universe remains balanced. The story is never deleted. It's only translated into a language we are just beginning to understand. Your watch keeps going. The silence is complete. It's not like space quiet, it's deeper, like sound just stopped trying. Above you, the whole sky is bent into a perfect, bright ring. A circle of warped starlight around a hole of pure black. That's the view from inside. You're the astronaut falling in. Your ship's instruments are humming, reporting numbers that feel less and less connected to anything real. The important number is on your personal clock. Your own time. For you, the trip from the event horizon to the center isn't endless. It's a countdown. For something huge like Sagittarius A, that countdown could be hours. Maybe a full day, a finite stretch of conscious experience. Outside, meanwhile, galaxies form, stars die, civilizations rise and fall over billions of years. Your last hours are their eternity. The equations that map your path are the geodesic equations. They're the math for freefall in curved spacetime. For a simple, non-spinning black hole, solving them gives a clear result. Your remaining proper time, tau, ties to a simple expression with the black hole's mass and where you started. The bigger the mass, the longer your subjective fall. But it's always finite. There comes a point deep inside where the gentle pull changes. The tidal forces, tiny at first, finally show up. For a supermassive black hole, this happens very late. Space starts stretching in the direction you're falling and squeezing from the sides. It's not an instant tearing, it's a slow, steady pressure. The universe's oldest light, the cosmic microwave background, is just a faint whisper from Earth. Now blue-shifted by your huge fall, it floods your senses as a blistering directional glare, a last warped echo of the Big Bang focused right into your path. You could picture a final log entry marked against that personal clock. Entry 1, the star ring is whole. Entry 10, the ring has gotten brighter, shifted blue. Entry 100, the tidal sensors show a slight difference. The forward screen is just a uniform, growing dark. Entry 1000, the cosmic background is now a searing arc. I can feel the pull, not as acceleration but as a deep tension in space itself. The philosopher Thomas Metzinger talked about consciousness, saying the subjective present is all that exists for the traveler. In here, that's absolutely true. Your past is a memory, your future is a location, your now is this shrinking capsule of sensation, speeding toward a boundary where sensation stops. This compression of the external future into your final moments is the ultimate isolation. You're watching, in fast forward, the heat death of everything you ever knew. But you're completely cut off from its timeline. Your story is ending while the grand story of the cosmos races toward its own distant finish. So we have to ask, if your conscious timeline ends at the singularity, does the journey mean anything? From outside, your story never quite finishes. From inside, it ends with total finality. Which perspective holds the truth of your experience? The answer seems to be that both do, in their own self-consistent frames of reality. Your meaning is locked inside your proper time, a private story the wider universe can never see. It's a story written in a diary that gets swallowed by the dark. And yet, in the holographic view, that diary's information isn't destroyed. It's stamped onto the horizon, a permanent part of the cosmic record. Your finite time becomes a timeless entry in a vast quantum code. That private story is in a diary the universe can't read. But what does the universe see? You're not the astronaut now. You're the distant observer. You're watching through a telescope. You've aimed it at a probe sent toward the supermassive black hole. At first, the signal is strong. It's clear. Then, as it nears the event horizon, something strange happens. The probe seems to slow down. Its light shifts to a deep red, a dim red. It fades, not like a light turning off, like an image receding into an infinite fog. It never quite seems to cross the line. You can wait a year, a million years, a billion. In any finite amount of time, the probe remains suspended at the edge. It becomes a ghost, frozen in time. This is the visual consequence, infinite gravitational time dilation. The event of the probe crossing the horizon is pushed to the infinite future. In what physicists call coordinate time, the time on your distant clock. From your vantage, the probe's clock has effectively stopped. As Neil deGrasse Tyson has put it, from our perspective, time at the horizon stands still. It creates an illusion. Theorists once called it a frozen star, an object eternally hovering at the point of collapse. The mathematics behind this uses the Schwarzschild time coordinate. The t in the equations for a simple black hole. That coordinate works perfectly for you far away, but as you track the probe's descent, a term in the equation goes to zero. A term involving distance from the center. This makes the relationship between your time and the probe's time diverge. The probe's journey becomes an asymptotic process. A curve that approaches a line it never touches. In your timeline, the crossing isn't an event that happens at a specific time. It's a limit, forever approached but never reached. Before it fades entirely, the probe passes through a region, the photon sphere. This is the distance where gravity is so strong that light itself can orbit the black hole. From here, light from the probe can loop around and still escape to your eyes. The last detectable image you'll receive won't be of the probe itself. It will be a smeared, distorted ring, its last light trapped in orbital loops before finally escaping. That blurry ring is part of what we see in the Event Horizon Telescope images. The warped glow around the shadow. This has profound practical implications. When we observe black holes merging like the events detected by LIGO and Virgo, we are seeing the final orbits from the outside perspective. The merger from the outside, the intense gravitational waves are emitted as the objects spiral in, but the actual moment each object crosses the new, combined horizon, that signal is, in theory, infinitely redshifted. Infinitely stretched, we never see that final plunge in our data. It's like watching a movie where the climactic scene is a single frame, a frame that holds forever, never advancing to the next. This forces a deep question, an almost philosophical question. If something never crosses the horizon in any finite time we can ever measure, does it ever truly enter? From the probe's own frame, it crossed long ago. It continued its journey. From your frame, it is eternally in the act of crossing. Both descriptions are mathematically valid. Within their own reference frames, this creates a paradoxical duality. It challenges the very notion of an event having a single, absolute time. It suggests that happening is not a universal fact. It's a perspective-dependent story, and if two observers can fundamentally disagree on whether and when a pivotal event occurs, what does that say about the solidity of reality itself? Reality doesn't tear, our maps do. Schwarzschild coordinates, the first ones we used for a simple black hole, they're like a standard world map. Far from the event horizon, they work fine. They give you a clear grid, space and time laid out, but right at the horizon, that map develops a singularity. The grid lines pile up infinitely. Time and space seem to swap places. The equations scream error. It's not that spacetime itself is broken there. It's that our language for describing it has hit a limit. The coordinates fail. Like a flat map distorting the poles into impossible lines, the terrain is smooth, our chart is flawed. To go inward, you need a better map, one that doesn't rip at the boundary. That's where exotic coordinate systems come in. Kruskal-Szekeres, Eddington-Finkelstein. Think of them as the polar projection of the black hole world. They cover the whole geometry smoothly, from the distant universe you left behind, across the uneventful crossing of the horizon, all the way down to the central singularity. They remove the coordinate singularity, the artificial tier, revealing a continuous landscape. In these coordinates, the event horizon is just another surface you pass through. Like crossing the Arctic Circle on a globe, nothing special happens to the geometry there. The violent infinity was a trick, a poor choice of words. These mathematical frameworks do something profound. They extend the spacetime manifold. They show you not just the black hole you fell into, but a maximally extended geometry. This mathematical extension can include mirror regions. Other universes, even white holes, are theoretical time-reversed black holes that spew matter out. It's a complete picture, elegant, drawn from Einstein's equations. But here's the crucial insight: coordinates are not reality. They're a language we choose. The Kruskal extension is a valid solution to the equations. But whether those other universes or white holes are physically real, that's a different question. The math allows it, nature may not. To visualize this causal structure, physicists use a Penrose diagram. It takes the infinite expanse of spacetime and squishes it into a finite diagram, preserving the light cones, the causal relationships. On this diagram, you can draw the entire history of a black hole and its possible extensions. Light rays travel at 45-degree lines. The singularity is a jagged boundary at the top. The event horizon is a diagonal line separating the interior from the exterior. This diagram makes it visually clear. Once you cross that diagonal line, every possible path, every future light cone points toward the singularity. No escape. Not even for light. It also shows how different coordinate systems simply cover different patches of this larger, unified diagram. At the heart of these tools are null coordinates. Coordinates based on the paths of light rays themselves. Since nothing travels faster than light, these coordinates naturally map out the causal structure of spacetime. They tell you what events can influence what other events. In the black hole interior, these coordinates reveal how your ability to communicate, to cause and effect becomes severely limited. And then terminates, so we have this beautiful, extended mathematical reality. But we have to remember the difference: analytic extension versus physical reality. The equations might paint a picture of an eternal, interconnected multiverse stemming from the black hole. But the physical processes, quantum gravity, the formation of the black hole from a collapsing star, likely cut off that elegant extension. The white hole and other universe segments may be mathematical artifacts, not destinations. This brings a reflective question, almost unsettling. If our most sophisticated mathematical frameworks can describe the interior of a black hole as a timeless, extended geometry, if they can smoothly chart a path through a region where time loses all common meaning, does that suggest time itself is just a mathematical artifact? A convenient variable in our equations rather than a fundamental substance of the universe? We use these coordinates as our best tools to speak about the unspeakable. To map the unmappable. They don't make the reality any less strange, but they give us a language, however foreign, to begin the conversation about where meaning goes when time dissolves. The Schwarzschild map was for a simple monster, a still one, but the universe prefers to spin. Most black holes, especially the supermassive ones at the centers of galaxies, they come from spinning stars. They inherit that rotation. In 1963, a mathematician from New Zealand, Roy Kerr, found the solution. The exact solution for a rotating black hole in Einstein's equations. It was a breakthrough. Kerr said later it was a gift, that the equations were so beautiful they just gave up their secret. His metric describes a cosmic whirlpool. And in that whirlpool, time doesn't just slow down, it gets caught. It gets pulled into a complex dance. The key is frame dragging. Imagine a spinning carousel, but instead of horses, it's spacetime itself. The fabric stands still near the edge and you're pulled along, forced to move with the rotation. A rotating black hole does that to the universe around it. It doesn't just pull on matter, it drags the grid of space and time with it. This creates a region outside the event horizon, the ergosphere. An oblate, pumpkin-shaped zone where the dragging is so powerful nothing can stand still. Every object, even light, is forced to move with the spin. In the ergosphere, something stranger happens to time. Paths that are normally timelike, the paths all matter must follow, moving forward in time, they can become space-like. The distinction between moving through time and moving through space gets blurred. You are compelled to move, as if time itself has a direction you must circle. This rotation changes the interior. The terrifying point singularity of a static black hole is replaced in Kerr's solution by a ring singularity, a one-dimensional ring of infinite density. But the geometry around it is bizarre. In certain regions, this ring becomes gravitationally repulsive. It acts as a barrier, not an attractor. The equations suggest if you could approach from the right angle, you might not be crushed. You could, in theory, pass through the ring, and what's on the other side? The math opens into a mirror universe or a tunnel, a wormhole to another region of spacetime. Whether that's physically real or a mathematical artifact is debated, but the possibility is written into Einstein's own equations. Deeper inside is another boundary. The inner Cauchy horizon, a horizon of predictability, cross it, and the deterministic power of physics breaks down. The future is no longer determined by the past. It's here that closed time-like curves could exist, those theoretical paths for time travel. You could, following the geodesics, loop back and meet your own past. But most physicists think this region is violently unstable. The slightest perturbation, a single photon falling in, would trigger an infinite blue shift of energy. Mass inflation, it would likely destroy the time machine before it could be used. Nature may have built a firewall against paradox. The rotation creates practical effects too. Because of frame dragging, stable orbits can exist much closer to a Kerr black hole. Matter can spiral in, releasing tremendous energy that powers the luminous quasars we see. The infalling matter forms a hot, magnetized accretion disk. The black hole's spin, coupled with those magnetic fields, can launch colossal jets of particles. The Blandford-Zenagic process, these jets stretching for thousands of light years, are some of the most energetic phenomena in the cosmos, all choreographed by the rotation. There's also superradiance. If you send a wave of light or gravitational energy toward a spinning black hole, and it scatters off the ergosphere just right, it can steal some of the hole's rotational energy. It escapes with more energy than it came in with. The black hole spins down slightly, and the wave is amplified. It's like pushing a child on a swing at the right moment. Each push adds energy. The black hole itself becomes an engine for amplification. So, does rotation create pockets where time regains a strange order? In a sense, yes, the furious spin imposes a new structure, a preferential direction. Time is no longer just falling inward, it's being whipped around in a vortex. The chaos of the interior is given an axis, a spin that adds layers of complex geometry to time's demise. The Kerr metric shows a black hole isn't just a grave for time. It can be a frenetic, spinning engine, where time's meaning is stretched and twisted and repurposed before the final curtain falls. And if rotation can create tunnels and mirrors in the math, what other doors might be hidden in the spin of reality itself? That furious spin gives you a kind of order, but it doesn't resolve the deeper conflict, the conflict over memory itself. You burn a book, the pages become ash and smoke. The story, the words, they seem gone, but in principle, if you could track every ash particle, every photon of heat, you could reconstruct the text. The information isn't destroyed. It's transformed. That's a core rule of quantum mechanics, unitarity. The universe keeps perfect records. In the 70s, Stephen Hawking applied quantum theory to black holes. He reached a shocking conclusion. When matter falls into a black hole, and the hole later evaporates through Hawking radiation, the information is truly lost. The radiation is purely thermal, like random heat from a stove. It carries no imprint of what fell in. When the black hole is gone, only this featureless glow remains. The cosmic ledger has a page torn out. History is erased. That was the black hole information paradox. It pitted the reversibility of quantum mechanics against the irreversible thermodynamics of black holes. If Hawking was right, then time evolution inside a black hole isn't just strange, it's fundamentally flawed. The universe would have a mechanism for forgetting. It was so troubling that physicist John Preskill made a famous bet against Hawking. Preskill said he was skeptical that the fundamental laws of physics respect unitarity only until you apply them to black holes. He believed information must be preserved somehow. For decades, this paradox seemed intractable. Then, in recent years, a possible resolution emerged. From the holographic principle and gravitational path integrals, it involves something called the island formula. The idea is the information about what fell in doesn't stay trapped inside. It's not lost in the radiation either. Instead, it becomes encoded in the Hawking radiation through a subtle, complex web of quantum entanglement with regions inside the black hole, regions called quantum extremal islands. These aren't physical islands you could visit. They're mathematical regions in the gravitational description, where the entanglement entropy contributions come from. To calculate this, theorists use replica wormholes. You make copies, replicas of the spacetime geometry, and you connect them through wormholes in the path integral, the sum over all possible histories. These wormhole connections show how information from the interior can be teleported, in a quantum sense, into the radiation outside. The radiation starts out looking random. But as more evaporates, the intricate entanglement patterns begin to reveal the original information. It's like a scrambled hard drive. To the untrained eye, the data is gibberish. But with the right decryption key, understanding the entanglement structure, you could reconstruct every file. This ties to another profound idea: computational complexity. Some physicists propose the growth of complexity inside a black hole might be the true measure of time's passage there. As quantum states become more entangled, more complex, they evolve. This internal complexity could keep increasing long after classical descriptions of time break down. It suggests that even when the geometry is chaotic, a quantum form of progression continues. These developments have reshaped the firewall debate. If information escapes smoothly via entanglement, there may be no need for a violent firewall at the event horizon. The horizon could remain a peaceful place to cross, while the quantum information about your journey is meticulously copied onto the outgoing radiation. The paradox softens, but the strangeness deepens, so we're left with a reflective question. If information is preserved, if the universe never truly forgets, does time inside the black hole retain a hidden quantum record of every event? Even as classical causality dissolves, could there be a subtler, more fundamental chronology, written in the language of entanglement and complexity? This paradox isn't just a technical puzzle. It strikes at the heart of whether time's passage has any ultimate meaning. Is the flow of time just the unfolding of quantum information? And if so, what happens when that unfolding reaches the ultimate limits of gravity? Information isn't lost, but meaning, that's different. People have been wrestling with time long before black holes. Heraclitus, he saw a river, always changing. You can't step into the same river twice. For him, reality was just flux, but Parmenides argued the opposite. Change is an illusion, he said. Reality is one thing, unchanging, timeless. Then later, Immanuel Kant, he said time isn't a feature of the world out there. It's a framework our minds impose, a condition we need to have any experience at all. It's how we organize sensation. These old debates, they come back inside a black hole. The interior doesn't just bend time, it challenges what time even is. It suggests time might not be fundamental. It could be emergent, a local phenomenon like weather in a valley. Not a property of the whole cosmos. The philosopher Hugh Price echoed Einstein. He wrote that the flow of time is a stubborn illusion that points to a divide. On one side, presentism, only the present is real, the past is gone, the future isn't here. Our experience screams this is true. We feel ourselves moving from one now to the next. On the other side, eternalism, the block universe from relativity. all of spacetime exists as a single, four-dimensional block. Your birth, your life, your future, they're all equally real. Just at different coordinates, you don't move through time, you simply are extended along a line. The black hole interior, with its warped causality, seems to favor this block view. The idea of a universal present breaks down there. Think of a DVD of a movie. The whole film is there on the disc. Every frame exists at once. That's the block universe. Playing the DVD is like consciousness. The laser reads the data in sequence, one frame at a time. It creates this vivid illusion of a story unfolding, of things happening. That laser is our perception, our awareness trapped in a narrow slice, creating the flow we call time. In the black hole, the player malfunctions. The frames get scrambled, the sequence loses order, and deep inside, the disk itself might be melting. The data is still there, maybe, but the coherent playback, the story of time, that ends. This touches being human, our sense of becoming things coming into existence, fading away. That's central to meaning. We celebrate beginnings, mourn endings. We make choices because we believe the future is open. That's the theater of free will. But in a timeless block, is the future already written? Are our choices just points on a line we're tracing? Some philosophers say even in a block, our experience of choice is real. The block contains the whole process of you weighing options. Your feeling of freedom is part of the geometry. But it's a difficult idea. It can feel like our self is just a story we tell, a necessary fiction that leads to the anthropic principle. We evolved in a pocket of the universe where time flows forward, where causality is clear, because only in stable places could complex things, stars, planets, life arise. We shouldn't be surprised to find ourselves where time seems real. It's the only kind of place we could be. The black hole interior is the opposite. It's so extreme we can't survive there, and there the mask slips. The illusion of flowing time, maintained by stable conditions, falls away, revealing a stranger, timeless substrate. So if time isn't fundamental, is meaning something we impose, the equations of quantum gravity might be timeless. But our lives aren't. We are the laser on the DVD. We create the narrative. We give moments significance. The black hole shows us the stage without the play. It shows the raw scaffolding, devoid of story, and that's humbling. It suggests the meaning we cherish, the arc of a life. A civilization isn't written into the cosmos's code. It's written by us, temporary inhabitants of a small, orderly corner. Our struggle to understand time's end in that darkness is, in a way, a struggle to understand the value of our own fleeting now. Our now is brief, but it's part of something much larger. Those supermassive black holes in the centers of galaxies, they're not accidents, they're architects. Their gravity pulls in the first clouds of gas. That gas forms the first stars, and the black hole's energy, its jets and radiation, it regulates everything. It can heat material around it and stop new stars from forming, or it can trigger star formation with shock waves. So these monsters dictate the life cycle of their galaxy. They're like a beating heart. The rhythm of that heartbeat, the inflow and outflow of matter, it sets the tempo for billions of stars. Their influence stretches across cosmic time. It shapes the structures we see. This connects to the greatest timelines, our universe's own beginning, the Big Bang. It has a parallel. The initial state was infinite density and temperature, a singularity. Mathematically, it's like the singularity inside a black hole, but in reverse. One is a collapse, the other an expansion. Cosmologists like Sean Carroll point out this gives us a clue about time's arrow. He notes the reason time points forward, from the low entropy Big Bang to the high entropy future. It might be the most important fact we least understand. The arrow of time isn't just a local rule, it's a cosmological property imprinted at the beginning and the end. The evidence suggests an expanding, cooling fate, a heat death. Entropy is maximized, all processes stop. time would lose all meaning because change ceases. Or if gravity reverses the expansion, a big crunch could happen. Another singularity, bookending history. In both visions, black holes are key. In a heat death, they'd be among the last structures to evaporate through Hawking radiation. Their final pops of energy would be the universe's last flickers of organized time. We can hear their influence. When two black holes spiral and merge, they don't crash silently. They send out ripples, gravitational waves. These are distortions in spacetime itself, traveling at light speed. LIGO, the Laser Interferometer Gravitational Wave Observatory, first detected them in 2015. The signal was a chirp, a rising frequency as they got closer. That chirp encodes the history of their dance. It's a direct imprint of how they warped time and space in their final moments. Listening to gravitational waves is like listening to time being twisted and released. Some theories push this further. The holographic cosmology conjecture suggests our entire expanding universe, with 3 spatial dimensions, could be a projection from a 2-dimensional surface in the past. This mirrors how a black hole's interior is projected from its event horizon. It implies the cosmos might operate on similar informational principles. Even more speculative is baby universes. The intense conditions inside a black hole singularity might not be an end but a bridge. A new spacetime bubble could pinch off, inflating into its own separate cosmos with its own laws and arrow of time. In this picture, black holes could be cosmic nurseries, each containing a universe where time flows in ways alien to our own. Picture the cosmic web. The vast filamentary structure of galaxies. At the intersections of these filaments, you find the greatest clusters, each with a supermassive black hole. These points are knots where spacetime is most severely curved, where gravity's grip is strongest. They're places where the fabric of time is pulled taut, twisted by the mass of millions of suns. The cosmic web isn't just a map of matter, it's a map of gravity's dominion, and therefore a map of where time is most profoundly sculpted. So we have to ask, if the universe has its own timeline from birth to death, do black holes act as punctures in that fabric, places where the normal rules of time leak away? Understanding their role shifts the perspective. The meaninglessness of time inside a black hole might not be a universal truth, it could be a local anomaly. A strange eddy in the vast river of cosmic time, a reminder that our experience of a steady, forward-flowing now, it's a gift of our particular place in a much wilder, more intricate temporal tapestry. We can't send a probe into a black hole, so we have to think. Einstein used thought experiments. He called one his happiest thought, a person falling freely, feeling weightless. That idea led to general relativity. We can take that elevator further. Imagine you're sealed inside a windowless capsule, falling toward a supermassive black hole. You feel weightless. No instrument inside can tell you if you're in deep space or falling toward the event horizon. That's the equivalence principle. It suggests the crossing could be smooth, uneventful, but thought alone isn't enough. We need to see the math move. That's numerical relativity. It's using supercomputers to solve Einstein's complex equations. Franz Pretorius is a pioneer. He said the goal is to visualize the invisible, to see spacetime ripple and tear. His team's simulations were the first to show 2 black holes merging completely. From inspiral to ring down, to do this, they divide spacetime into a computational grid, millions of points. At each point, the computer calculates the curvature, how it changes and how that change affects neighboring points. It's a colossal feedback loop, gravity bending gravity. These simulations show the black holes colliding. They reveal the dynamics of their event horizons, how they stretch and merge into a single, distorted shape. They let us peer, virtually, at the chaotic geometry inside the newly formed black hole. There's a landmark effort, the Simulating Extreme Spacetimes Project, SXS, Their visualizations of black hole mergers aren't just pictures, they're rigorous solutions to Einstein's equations. The intricate details in their simulations were crucial for interpreting the first gravitational wave signals from LIGO. That work earned a Nobel Prize. When you watch their video of two black holes spinning together, you're watching a prediction of how spacetime itself behaves under extreme stress. It's a glimpse into a violent choreography, a dance in a region forever hidden from direct sight. But can we bring any of this physics down to Earth? In some ways, yes. Through analog models, researchers create analog black holes in labs. They don't use gravity, they use other media that mimic key properties. One classic experiment uses a tank of flowing water. If the water flows faster than the speed of surface waves, those waves can't travel upstream. That creates a sonic horizon. Like an event horizon but for sound, experiments have even reported detecting a form of analog Hawking radiation in these setups, phonons, sound particles emerging from the horizon. Other experiments use ultra-cold clouds of atoms, Bose-Einstein condensates. Light can be slowed to a crawl there, creating optical horizons. These tabletop models let us test ideas. How horizons behave and radiate in a controlled setting. Looking ahead, perhaps the most powerful tool will be the quantum computer. The goal is to use qubits to simulate the quantum states of spacetime itself. To run experiments on a theory of quantum gravity we can't yet write down fully. It's a tantalizing future. We might one day code a virtual black hole. And watch from the outside how information scrambles on its boundary. All of this, the thought experiments, the supercomputer visualizations, the analog labs. It serves one purpose. It bridges a gap, the unbridgeable gap between our theories and an inaccessible reality. They are probes made of mathematics and imagination. So we return to the question, can a simulation, no matter how advanced, ever tell us what time truly means inside that darkness? It can show us the geometry, the causal structure, the flow of information, but the raw, subjective experience of time, the silent countdown of an astronaut's own clock, that remains locked within the event horizon. These experiments give us the map, but the territory with all its terrifying and beautiful meaning, that's a story the universe tells only to those it consumes. The territory is a story told only to the consumed, but if the one being consumed is conscious, a mind with its own internal clock, falling into that silence. Neuroscience tells us our sense of time is fragile. It's not a pipeline to some universal tick. The brain builds it moment by moment from electrical pulses and chemical signals. Cognitive scientist David Eagleman says time is a constructed property of the brain. It weaves together sight and sound and memory and expectation into a seamless flow. That flow is the present. This constructed now is what you'd carry across the event horizon, your last tether to order. Inside, the environment dismantles the very materials the brain uses to build time. First, the external cues vanish. The day and night cycle is gone, replaced by that warped, unmoving ring of starlight. Then darkness, no regular events. No predictable sounds. The universe's background hum gets stretched into silence. Then, deeper in, causality itself blurs, the link between action and consequence. The sequence that gives events their place in a timeline, it unravels. Your brain relies on predictable sequences to calibrate its internal clock. Without them, that clock malfunctions. We see glimpses of this breakdown right here on Earth. In extreme isolation experiments, cave explorers who live in timeless darkness. After days, their sleep-wake cycles stretch and twist. Their estimates of elapsed time become inaccurate, wildly inaccurate. Minutes feel like hours. Hours collapse into an instant. They report vivid dreams. Hallucinations, a profound disconnection from the outside world's rhythm. And this is with Earth's gravity still gently tugging. with their own heartbeat as a metronome. Now magnify that, remove all reference points, place a mind where space itself is falling, where light from the outside universe compresses the future into a single flash. Where geometry suggests cause can follow effect, the brain's time-keeping machinery would have nothing left to latch onto. What might that distorted perception feel like? One possibility is subjective time dilation, where moments stretch into seeming eternities, not from physics but from a starved brain filling the void with its own noise. Hallucinations could become the only events, their bizarre logic replacing the lost narrative of causality, or the sense of time might simply evaporate. Replaced by a perpetual, undifferentiated present, a silent, expanding now, no past to anchor it, no future to anticipate. Philosophers discuss the concept of a philosophical zombie in timeless environments. A being that functions but has no subjective experience of sequence. It's a thought experiment. It asks if consciousness requires a consistent timeline to exist at all. This forces a question. If time is a story the brain tells about change, what happens when change loses all coherent structure? Could a mind perceive timelessness? Or would it, in its desperate need for narrative, impose a false time onto the chaos? A private, hallucinated chronology that ends only when the biology supporting it is torn apart by the tides of gravity. This intersection is where objective physics meets subjective reality. The equations describe the collapse of time as a coordinate, but a conscious being would live that collapse as an experience. So perhaps the final meaning of time inside a black hole isn't in the curvature of spacetime. It's in the fading echo of a brain's last attempt to make sense of a universe that has stopped making any. The fear of a story ending, of a mind fading out, that's an old fear. People felt it long before they knew what stars were. They told it in their myths. Time ending, a void that takes all order. The Greeks called it chaos, that gap formless before the cosmos. Buddhism has sunyata, emptiness, the void beyond all concepts. These aren't just nothing, they're where reality's rules dissolve, the abyss that eats time, and now we have a scientific name for that: black holes. The ultimate unknown, where order stops. Joseph Campbell said the cave you fear to enter holds the treasure. For ages, that cave was the underworld, the prison, the journey into darkness where the hero faces oblivion. Now that cave is a gravitational pit in space. Our equations, our spacecraft, they're the torches we carry in. Look at the symbols, the Ouroboros, the serpent eating its tail, ancient symbol for cycles, for eternity, a system consuming itself. A black hole's event horizon, the inward flow of spacetime, it's a perfect Ouroboros. Matter and light spiral in, feeding the darkness, a one-way cycle. And creation myths, they often start with a void, a stillness everything comes from. The singularity inside a black hole is that modern void, a point where our physics breaks and where some theories say new universes could be born. That duality is in the Hindu deity Shiva, destroyer and creator. Shiva's dance sustains creation, preservation, dissolution. A black hole destroys stars, information, time itself. But in the math of quantum gravity, it's also a potential creator, a seed for new order. It holds both roles in one point. Our stories prepared us for this. The hero's journey is a descent into the unknown, trials that strip the old self away to return transformed or not return. An astronaut's theoretical plunge is the ultimate literal version, a journey with no return. Science fiction gets this. In Interstellar, the black hole gargantua isn't just a plot device. It's the labyrinth, the underworld, the place beyond where the rules of love and gravity tangle. It uses the black hole's time dilation as an engine for sacrifice and connection, and confronting a black hole's infinity does something to the mind. It's like the sublime terror of a vast canyon or a stormy sea. It dwarfs us, reminds us our order is temporary, fragile, in a cosmos of such extremes. Artists try to capture that feeling, rendering singularities not as points, but as radiant knots, dark vortices, gates of light, metaphors for a reality you can't depict literally. So the question, did our ancient stories of chaos and the abyss just prepare us for this scientific truth? In a way, yes. They're the human mind over thousands of years, mapping the edge of the knowable. The black hole is the physical form of that edge. Our myths are the treasure Campbell meant, not a physical prize, but the human capacity to look into the cave of ultimate mystery and try to understand what we see there. This lens shows our fascination with time's end isn't from modern astrophysics. It's a timeless thread in the human story, woven long ago, now lit by the cold, beautiful light of science. The next decade could change how we understand black holes. What's inside them? That's the idea behind a new set of tools. They're not built to see light. They're built to listen to the vibrations in spacetime itself. The main project is called LISA, the Laser Interferometer Space Antenna. It's 3 spacecraft. They'll fly in a triangle millions of kilometers apart. They'll form the most sensitive gravitational wave observatory we've ever made. Right now, detectors like LIGO listen for high-pitched sounds. The chirp of smaller black holes colliding. LISA will tune into lower frequencies. The deep hum of supermassive black holes. These giants orbit each other for years before they merge. That sound will let us map the spacetime around them in detail we've never had. We'll hear the final spiral, the merger, and then the ring down, the black hole settling like a bell that's been struck. Each ripple is a direct message. It comes from the warped geometry near the event horizon, and it carries clues about the singularity it hides. This is part of a larger convergence: observational astronomy, theoretical physics, even quantum computing. They're all coming together. The Event Horizon Telescope, the one that gave us that first shadow image, it's upgrading. Adding more dishes around the globe. The goal is to make sharper movies of the chaotic plasma orbiting Sagittarius A. We might see flares, hotspots dancing around the void. That would test how matter behaves in the most extreme gravity. But to understand those signals, we need better theories. The frontier of string theory and loop quantum gravity is trying to describe what replaces the singularity. Is it a fuzzball, a quantum bounce? The equations are getting more precise. They're starting to offer predictions about the information that escapes. Then there are the lab experiments. The vision is a tabletop setup, something that creates a microscopic analog of a black hole's quantum behavior, not with real gravity but with controlled systems. Ultra-cold atoms or manipulated light. Researchers want to simulate how information gets scrambled, how data thrown into a black hole gets mixed up and encoded on its boundary. Some even hope to create synthetic Hawking radiation, watching as particle pairs emerge from an artificial horizon, and a quantum computer, programmed the right way, could one day simulate the entanglement of a tiny patch of spacetime, letting us run experiments on theories of quantum gravity we can't fully write down yet. The key questions are still there. Is the mathematical singularity real, or is it always resolved by quantum effects? What exactly happens step by step to information that falls in, and can we ever detect a definitive signature of the interior? From the safety of the outside universe, some theorists are looking for subtle imprints in the gravitational wave ring down, a faint echo, something that might betray a surface or a quantum structure just inside the horizon. Others are scrutinizing the statistics of Hawking radiation, looking for any tiny deviation from pure randomness, a hidden message in the heat. This leads to a kind of tension. A reflective one. Will we ever truly know what happens inside a black hole, or is the interior by its nature forever hidden from any outside observer? The cosmic censorship hypothesis suggests the universe hides singularities behind horizons for a reason. to protect the logical order of causality outside. Maybe some truths are fundamentally veiled, but the drive to lift that veil, to peer into the abyss, that's what gives the quest its meaning. The answers might lie beyond the reach of time as we know it. But the search itself expands what we can understand. It reminds us that we're part of a cosmos vast enough to contain mysteries that humble us, and clever enough to build the tools to start unraveling them. Looking into that kind of abyss has a cost. If we ever try to send a probe into a black hole, a real machine, not just an idea, it forces a hard question. Should we even go near it? The ethics are difficult right away. You'd be putting enormous resources, energy, human effort into an experiment where, by the laws we know, nothing comes back. It's the final scientific sacrifice, sending our questions into a fire to be burned up, that brings a deeper unease. Is some knowledge just off limits? Is there a point where curiosity is like trespassing, like opening something you can't ever close? A science ethics panel wrote once that the drive to understand needs to be balanced with respect for the unknown. And with a clear look at what might happen, even if it seems far off, the risks, even if they're only theoretical, have to be thought about. Could poking at the event horizon with technology we can't imagine yet somehow shake the local spacetime? Could we accidentally make an artificial singularity that's unstable? The energy needed makes it sound like a story, but the idea stands. When you interfere with the basic forces, things can become unpredictable. There's the example of the Manhattan Project. The effort to understand the atomic nucleus unlocked a terrible power. It changed global politics and human safety forever. It's a lasting lesson that unlocking nature's secrets comes with a heavy responsibility, but then the other side is strong too. We've always gone into the unknown. The first deep-sea divers went down into total darkness with no promise of coming back. The first astronauts rode explosions into empty space. Those efforts came from a belief that the value of knowing and the act of exploring made the risk worth it, and from them came huge benefits for society. Spin-off technologies in materials, medicine, computing, things that changed daily life. A black hole mission, even a doomed one, would force our engineering to extremes we can hardly picture. It would probably lead to breakthroughs we can't see yet. And past the practical stuff, there's what it means to people. A mission like that would be a statement that the human spirit won't accept apparent limits. It would capture the imagination of generations, inspire new scientists, engineers. It would tell a story not of fear, but of brave questioning. The probe itself, in its last signal before the signal stretches forever, would become a monument. Like a message in a bottle thrown into the darkest sea, saying, "We were here and we tried to understand." So you come back to the main question: is it worth the cost to understand the end of time? The answer might not be a simple yes or no. It might be in the balance we try to find, to move forward with humility, with strict safeguards, and with an open talk about why we want this knowledge. Is it for power, for use, or is it for a more fragile, basic reason that to look up and wonder is part of who we are? The black hole asks us to define not just physics, but our civilization's values. It asks if we can stare into the place where meaning falls apart and still find meaning in the act of looking, explaining time's death inside a black hole to a classroom. It's a profound challenge. How do you make the infinite tangible? How do you sketch the unspeakable on a whiteboard? Richard Feynman said if you can't explain something simply, you don't understand it well enough. That's the guiding principle here. The goal isn't the full mathematical terror. It's to build a conceptual bridge, a bridge strong enough to carry a curious mind to the edge. The first tool is the analogy, a powerful, imperfect tool. The classic is the rubber sheet, a stretchy fabric for spacetime, a heavy ball in the middle creating a gravity well. Students roll marbles to see orbits. They watch a marble spiral in, showing the inescapable pull. For time dilation, teachers might use a metronome, Imagine two identical metronomes ticking in sync. Place one near the weighted center of the sheet. As the fabric stretches, the ticking slows. It's a visual metaphor for how gravity stretches time. These models are flawed. The sheet uses gravity to simulate gravity, but they create an intuitive hook. They make an abstract geometry feel almost tactile. Then come the simulations. Modern planetarium software can visualize a fall into a black hole. Students don't just hear about warped starlight and a frozen clock, they see it. They watch from their seats as a virtual spacecraft approaches the event horizon. The forward view darkens while the universe behind compresses into a brilliant, shrinking ring. These visual narratives are unforgettable. They translate equations into experience. Interactive websites let users adjust a black hole's mass and spin, then see in real time how the event horizon grows or how an astronaut's clock diverges from Earth. This playful experimentation builds intuition faster than any lecture. Thought experiments turn students into participants. A classic is time dilation tag. One student plays a distant observer with a stopwatch. Another plays an astronaut falling toward a black hole, holding their own watch. As the astronaut walks slowly toward a marked event horizon on the floor, the distant observer's stopwatch is clicked rapidly, while the astronaut's is clicked slowly. The physical act demonstrates the relational weirdness. Both are correct in their own frame, yet they disagree completely on the passage of time. Another exercise tackles the block universe. Have students draw their life as a long, static ribbon, a world line, on a massive class-created spacetime diagram. It challenges the deep-seated feeling that only the present is real. A major part of teaching this is correcting misconceptions. The idea of a black hole as a cosmic vacuum cleaner, endlessly sucking in everything. Educators clarify that its gravity is simply gravity. If our sun were replaced by a black hole of the same mass, Earth's orbit would remain unchanged. We'd just be very cold and very dark. The sucking is a powerful narrative, but it misleads. The real drama isn't suction, but the warping of the stage upon which everything plays out. Linking these concepts to popular media, like the film Interstellar, provides a shared reference point. Discussing what the movie got right, the time dilation on the water planet, and what was artistic license, the Tesseract library inside Gargantua, sparks critical thinking. It shows science in dialogue with storytelling. At its heart, this education aims to foster a sense of profound wonder, not fear. The best planetarium shows don't leave audiences feeling doomed. They leave them feeling awestruck by the sheer scale and mystery. The educator's role is to guide that awe toward understanding, to replace the monstrous, cartoon black hole with a real, albeit terrifying, object of scientific inquiry. This leads to a reflective, almost unanswerable question. Can the true experience of timelessness, the subjective dissolution of sequence and causality, ever be communicated? Or is it like the color red to someone born blind, something that must be felt to be known? We can describe the equations, run the simulations, and act out the thought experiments. We can understand the mechanics of the clock stopping, but the inner reality of a timeless state may forever lie beyond the horizon of language. Yet, the attempt itself is what matters. By teaching the unthinkable, we ensure this profound knowledge doesn't remain locked in academic papers. It becomes part of our shared story. It enriches our collective imagination, preparing a new generation to ask the next questions, to build the next tools, and to keep looking into the dark, not with dread, but with a torch of relentless curiosity. That personal feeling, that fading, it becomes part of something much larger. When they first showed the image of the black hole in Galaxy M87, the astronomers in the room didn't cheer. They just sat there in silence. There was triumph, sure, a technological marvel, but more than that, there was this profound humility. They were looking at a shadow. A shadow cast by a monster 55 million light-years away. It confirmed a prediction made a century before, and in that shadow was a feeling: awe. Awe is the emotional response to vastness, to something that overwhelms what we currently understand. It expands our perception. It makes the self feel small and yet connected. Connected to something immense and incomprehensible. This feeling, it sits right at the heart of scientific inquiry and spiritual inquiry. It's the engine of curiosity. Carl Sagan said it. He said, somewhere something incredible is waiting to be known. The black hole is that incredible something. It's the ultimate limit of human knowledge. A place where our theories just dissolve into question marks, and that limit, it doesn't stifle creativity. It ignites it. Think about the psychological benefits of awe. Studies show it can reduce stress, increase feelings of generosity, make us more collaborative. It shifts our focus away from the narrow self, gazing at the Milky Way. Standing before a vast canyon or contemplating a black hole's event horizon, these experiences pull us out of our daily worries. They place our brief lives inside a grand, majestic narrative. The mystery of what's inside a black hole, it doesn't just puzzle physicists, it inspires artists, musicians, writers. It becomes a symbol, a modern-day myth for the edge of reality. This cosmic perspective is a gift. It reminds us that our world, with all its conflicts, is a tiny stage, a fragile stage, in an unimaginably vast and ancient cosmos. This sense of awe, it often starts young. There's the story of a theoretical physicist working on quantum gravity now. As a child, they found a library book with a painting of a black hole tearing apart a star. They were terrified but also mesmerized. That image sparked a lifetime of questions, not just how but why. What does it mean for a universe to contain such things? That childhood fascination with the ultimate unknown became a career dedicated to mapping the boundaries of the knowable. That's the role of mystery. It doesn't halt science, it propels it forward. The black hole information paradox isn't a wall, it's a beacon, drawing in generations of brilliant minds to wrestle with it. Every attempted solution, even the failed ones, it deepens our understanding of space, of time, of information itself. There's a deep humility required here, too. A humility in accepting that some truths may be forever veiled by an event horizon, that we may never get a signal from the other side. This acceptance isn't surrender. It's a mature recognition of our place. We are finite beings trying to decipher an infinite puzzle. The black hole teaches us to be comfortable with the question mark, to find wonder not just in the answers we have, but in the profound depth of our own ignorance. So then we return to the human scale, to our fleeting moments. In a universe that contains regions where time itself becomes meaningless, does that make our own experienced time more precious? The contrast is stark. Inside the black hole, causality unravels, sequence dissolves. Here, on this pale blue dot, we have a coherent story. We have a past we can learn from, a present we can act within, and a future we can shape. The very fact that time can end in such a bizarre way elsewhere, it highlights the incredible temporary order we inhabit. It frames our brief lives not as insignificant but as rare, as valuable chapters in a cosmic story still being written. This emotional connection, it transforms abstract physics into a human story. It's not just about curved spacetime and quantum foam. It's about what those ideas do to us, how they make us feel, how they expand our minds and connect us to the universe. In a way that is both intellectual and deeply felt. The black hole, in its silent, dark majesty, it ultimately holds up a mirror. It shows us the limits of our understanding. And in doing so, it shows us the boundless reach of our wonder. Time starts as this steady river, reliable, something you can count on, but then you follow that river all the way to a black hole. And it doesn't just bend, it evaporates. The whole story of time, which makes so much sense here, just turns into gibberish at the center, and that comes from 5 things working together. 5 principles. There's the extreme time dilation, where a clock stops completely from the outside. There's the reversal of space and time, where your future becomes a place you're moving toward. The singularity, where all our physics just breaks down. The loss of causality, where cause and effect get scrambled. And then the observer dependence, where now isn't a shared moment anymore. It's something personal, isolated. These aren't separate, they're a cascade, a domino fall. The extreme dilation at the horizon severs your timeline from the universe's. The role reversal inside locks you on a rail toward the center. The singularity erases the stage. The loss of causality cuts the thread that turns a sequence into a story. And the observer dependence shatters any single account of what happened or when. Each one feeds the next. It's a closed loop of disintegration, and you see a deep interplay here between our two great theories. General relativity, with its smooth geometry, gives us the dilation, the reversal, the singularity. It paints this picture of geometric fate, but then quantum mechanics insists information must be preserved. It suggests that classical picture is an illusion. The singularity might be a fuzzball. Information might be scrambled on the horizon. That tension is where the real mystery is. It's like having two translations of the same text, and they tell completely different stories about the ending, which leads to the tension between perspectives. From outside, time for someone falling in freezes at the horizon. The story is paused forever. From inside, their clock ticks normally right up to the end. Both are correct in their own frame. This isn't a puzzle to solve. It's a feature of reality in such extreme gravity. What happens isn't an absolute fact. It's a story that depends on where you're telling it from. Our language, built for an orderly world, fails at this edge. Imagine a clock not just stopping, but melting. The hands droop, the numbers blur and run together until nothing's left. That's the fate of time's meaning in there. So after following this to the edge, a question stays. Can we see our own steady time the same way again, knowing that in the heart of our galaxy, there are places where this framework dissolves? Does that make our daily seconds seem different? More precious, maybe. This synthesis of chaos isn't an ending, it's a preparation. It clears the ground to look at what's left when time itself is stripped away. The river of time doesn't just end, it changes. We've followed it all the way to the edge of what we can know, watching reality bend and slow, and finally fade away inside a supermassive black hole. We started with Einstein, with the idea that time is relative, that it's part of the fabric of spacetime, and we saw how, at the event horizon, a clock seems to stop from the outside. It just freezes there, but if you cross that line, everything shifts. Space and time swap roles. Your future isn't a spread of choices anymore, it's a place. It's the singularity, and at that point, our math stops working. Cause and effect come apart. The sequence that makes events mean something is gone. Then there's the quantum idea, that information might be saved on a surface like a hologram. Which could mean time isn't a fundamental thing. It might be a story that emerges from something else. These aren't separate curiosities, they fit together. They show that in these extreme places, our most basic idea, a time moving forward, doesn't just bend, it dissolves into paradox, into deep uncertainty. And that shows us black holes aren't just cosmic vacuums, they're laboratories, the universe's ultimate testing grounds where the rules get stretched to the absolute limit. Making us ask the deepest questions about existence, about information, about reality itself. Stephen Hawking spent his life on these questions. He said the greatest enemy of knowledge isn't ignorance. It's the illusion of knowledge. Looking into a black hole fights that illusion. It humbles you. It shows you how much we don't know. And in that humility, there's a kind of freedom. The freedom to wonder, to keep looking. So let this sit, not as something frightening, but as a wider view. When you check your clock tomorrow or feel the day rushing by, think about the contrast. Here in our stable corner of space, time gives us a structure for memory, for growth, for our stories. But out there at the galaxy's heart, that same structure can be twisted into a knot and made to disappear. That difference doesn't make our moments small. It makes them rare and precious. It sets our brief, coherent story against a background of cosmic chaos. It highlights this temporary order we get to live inside.